Okay, this is section 4.2, the mean value theorem and the first derivative test. So, the mean value theorem says if y equals f of x, that's some function of x, is continuous for every point, and this is a very important if. I misspelled continuous. Continuous for every point on the interval on the interval AB. So this is just 2x coordinates. And this is a closed interval, so it includes the endpoints. And it is differentiable at every point. So meaning the derivative exists, so it's smooth. Um, so this doesn't have to be the endpoints, but it does have to be every point in between. Then there is some point and I'm going to explain what this means here in a second. And I'll draw a graph to illustrate it. Oops. So the C is somewhere between A and B. So what this is saying, this f prime of c means the instantaneous slope, or the derivative. The derivative at a point, that's the slope of the tangent line. Saying the tangent line is equal to, this is the average rate of change, here this f of b minus f of a. That's the average rate of change, or the slope. So the slope, or the average, at the secant line is equal to the slope of the tangent line at some point. So here I've got 2 points, A and B. And I've got some function that does something between them. It has to be continuous and differentiable. My average rate of change here, we'll make a better line, is that it has a slope. Somewhere, there exists somewhere in there, and with that, having it a smooth curve, which is differentiable, there's going to be some point in here where the instantaneous rate of change, this particular is equal to the average. This particular example probably has two, so one down there, one up here. It doesn't have to have two, it just says there has to be one. So even if it's a straight line, there's all kinds of points then. But any curve will have that. If it's discontinuous, my graph A and B here, if it doesn't have to be continuous, then I can have that and this. Clearly that does not have anywhere where the slope meets. If it doesn't have to be differentiable, nowhere where it's going to meet that. So that if condition, very important. Can be continuous but not differentiable. Nowhere do I have a slope that meets that. It's not differentiable up here at this sharp corner. But if the conditions are met, it's got to be a smooth curve somewhere the instantaneous must eat the average. That's what the mean value theorem says. That's all the mean value theorem says. Don't make the mean value theorem complicated. So how do I apply it? Well, I've got a function f of x equals x squared, and I have an interval 0 to 2. That function is continuous on that interval, and it's differentiable. Its graph is going to look like this, goes through the point 0, 0, and 2, 4, and we know it curves up. So we'll go ahead and find, it's going to be somewhere in here, f prime of x equals 2x. The f of b minus f of a, f of 2, so this is really just a glorified slope formula. y2 minus y, f of 2 is just y2 minus y1. F of 2, 2 squared is 4. It's a slope formula, you just actually have to find the y-coordinates. So now I set this equal to that, and I get 2 equals 2x. Clearly we can see x equals 1 or c equals 1. If I'm looking at f prime of c, I could say that the function is 2c. Probably should do it that way. 2c, c equals 1. Okay? Pretty basic one. My next one will be f of x equals the square root of 1 minus x squared. It says find the tangent to f in the interval negative that is parallel to the secant. That's essentially the mean value theorem. So this is essentially x squared plus y squared equals 1, but it's half of it. It's a semicircle. If I connect those dots, the the points are negative 1, 0, and 1, 0. And I get 0 minus 0 over 1 minus negative 1. 0 over 2. A big fat 0. My slope is 0. I can probably potentially look at it and see that my tangent is 0, right at 0. I get a maximum here. It's top of a semicircle. But I can also do this. F prime of x. Well, this is a square root. So 1 half 1 minus x squared to the negative 1 half times the derivative of the inside, negative 2x, giving me negative x over square root of 1 minus x squared. So the 2's cancel, the negatives don't, the x goes to the top. And I know this has to equal 0. Well, to solve, I'll multiply both sides by the denominator. And this lovely thing happens when I multiply by 0, it's still 0. So x equals 0 is my c is 0. Example 3 is going to say if a car is accelerating from 0 takes 8 seconds to go 352 feet. Its average velocity is 352. So it takes 8 seconds to go a total of 352 feet. Its average velocity is total feet divided by time, and that reduces to 44 feet per second. Okay. At some point during this acceleration, this is approximately 30 miles per hour. It says some point during this acceleration, the car must read 30 miles per hour. That's its average speed. Clearly, it crossed that speed, so it must actually read that. Hopefully, that makes logical sense. So that is the mean value theorem. Again, it's not complicated. It's find the slope between the 2 points, set the slope equal to the derivative, and solve for x, or plug in c and solve for c. The first derivative test says if f prime of x is greater than 0, meaning we get a positive number, then the function is increasing. What does that mean? First derivative is positive, means the slope of the tangent line is positive. That means the function must be going up. It also says if f prime of x is less than 0 or negative, it means I have a negative slope of the tangent line, then my function is decreasing. And I can apply this to anywhere where the first derivative positive is an interval of increasing. My interval of increasing is also going to include my endpoints. So it's going to include where it's 0. Okay? My interval of decreasing also includes my endpoints because they increase and decrease through that point. Once you pass the point that it stops. So looking at the function y equals x squared. Y prime equals 2x. How I find my intervals of increasing or decreasing, I gotta find where it's 0. Because where it's 0 is where it's going to switch, theoretically, or potentially touch. But it's 0 at x equals 0. And hopefully you remember from um, at making these sign plots. Because we did a little bit of this um, did just a little bit in free calc. So now I'm going to take a look here. Y equals 2x. I'll plug in a negative number. When I get a negative number, I get a negative value for y prime. So number less than 0, like -1, I get y prime is -2. That's negative. All I care about is the sign because I'm comparing it to these two clauses. If I look at y prime equals positive number like 1, 1's an easy one, that's a positive. This happened to be a very easy one. So this function is increasing. The only place where it changes is at 0, from 0 to infinity. It is decreasing from -infinity to 0. Notice the including 0 on both. Let's apply this to a little more challenging one. X cubed minus 4x. We'll make that a meter cubed. F prime of x is then equal to 3x squared minus 4. So in order to find where it switches, I need to have these. Um, I need to set it equal to 0. And I'm going to solve. So I add 4 to both sides. I divide by 3 on both sides, and I get 4/3 equals x squared. I will now square root both sides, and I get plus or minus the square root of 4/3 is my x value. So I set up my first derivative sign plot. I've got negative square root of 4/3. I've got positive square root of 4/3. So I just have to look at my signs. So I'll take something like -2. That is to the left, on the left side here of the 4/3. -2, plug it in, 3 times -2 squared minus 4. That's 4. 12 minus 4 is 8. That's a positive. Easiest number between these two is 0. That's 0 minus 4 is a negative. And easiest number to the right of 4/3 is probably 2. Again, 12 minus 4 is 8. That's a positive. So looking at my function, where it's positive, it is increasing. It's positive from negative infinity to negative square root of 4/3. Union, I'm running out of space, so I'll use another line. Square root of 4/3 to infinity. Again, including both endpoints. It's decreasing where it's negative. Which again, including the endpoints, square root of negative 4/3 to square root of 4/3, it is decreasing. This will lead into curve sketching in tomorrow's lesson. Square root of 4/3, something like this. That does go through 0, 0. I'm increasing to square root of 4/3. I decrease, and then I increase again. And we can see that on the graph. You could use a calculator to graph that. You will get something that looks roughly like that. Notice I put no y coordinates on there. When we curve sketch, we'll pretty much avoid most of the y coordinates, except maybe some intercepts. Okay, that is section 4.2.